Hi, I am Felipe André Zeiser, and today I will present our work, Convolutional Neural Networks Evaluation for COVID-19 Classification on Checks Radiographs. This work is authored by Felipe André Zeiser, Professor Cristiano André da Costa, and Professor Gabriel de Oliveira Ramos. The early detection of COVID-19 is essential for proper treatment, and the transcription polymerase chain reaction RT-PCR is the gold standard for diagnosis. As an alternative to the RT-PCR, radiological examination such as computed tomography CT and checks X-ray CXR can be used to detect COVID-19. The CXR images have a lower sensitivity when compared to the computed tomography images. However, CXR has some advantage over CT examinations. We can highlight that CXR is more common in underdeveloped countries, have a lower cost, and reduce the probability of cross-contamination. Our goal is to evaluate convolutional neural networks architectures for the X-ray classification of COVID-19. So we have chosen 6 pre-trained convolutional architectures, the Inception ResNet v2, Inception v3, MobileNet v2, ResNet 50, and VGG16, and also Exception. In the literature, there are several related works. However, most of them are based on small datasets, evaluate the models in the validation sets, and few carried out multi-class classification. Thus, our contribution is evaluating 6 convolutional models for multi-class classification of COVID-19 in a dataset with more than 5,000 CXR images. We intend in the future to validate the proposed system in hospitals and also share the source code and the model weights on GitHub. Our pipeline is composed of 4 stages. First, definition of datasets. Second, preprocessing with resizing and normalization of the images. And then we do a data augmentation step to generate synthetic images. And finally, we training and testing the convolutional models. Our work uses 2 datasets. The first is COVID checks X-ray dataset, and the second is the checks X-ray images for classification. We have also created 3 sets, the first for training, the second for validation, and the last for testing. The meta-parents of each CNN architectures used in our work are present in the table 2. We have adapted some meta-parents for each model. So we have used a learning rate for each model to avoid overfitting. Also, we have adjusted the batch size according to our available hardware capacity. Finally, the depth of the networks was the same as in the original works. We have trained each convolutional model for 100 epochs, and when we analyze the results in the table 3, we can see the relative stability of the performance metrics, and we have the most significant variation for sensitivity between the MobileNet and Exception models, with a 6.34% of variation. For the specificity, the most significant variation was 6.33%. In general, the Exception model gives us the best results, except for the ALK. The best performance of the Exception model can be associated with the organization of convolutional blocks, which reduce the computational cost for training without reducing the number of trainable parameters. So, as conclusion and future work, we compared 6 convolutional architectures to detect COVID-19 in CXR images, classifying the CXR images into 4 classes: normal, viral, bacterial pneumonia, or COVID-19. As future work, we intend to analyze the use of explainable artificial intelligence to present the experts with suggestion of the characteristics considered during the inference process. Finally, the use of multimodal data can be helpful for context learning. So, we appreciate our attention. If you have any question, please contact us by email.